All right, thanks everybody for joining. So today we have Mohsen from Arizona State University. Mohsen is visiting us from the binary analysis group over there with Jan and Fish that some of you already know. And today he's going to talk about IoT firmware fuzzing. Well, I'll leave it to you from there.
Okay, sure. Okay.
This is too close, I can barely see it. Just see.
Cool. So, hi, thanks Christopher for introducing me. Again, so my name is Mohsen. I'm coming from Arizona State University. I'm finishing my master there, and so I'm actively looking for a PhD position for fall 2020. My talk is going to be about the evolution of the firmware fuzzing and analysis. So I'm gonna start with a little bit history about the firmware analysis and actually what firmware is, and then a little bit talk about the symbolic execution and so the way that we apply this technique to solve this specific problem, and also the evolution of the firmware analysis that I'm gonna go through the two papers that basically talked about the specific, they try to solve this problem using this specific technique, which we are focusing more on that, which is symbolic execution. There are a bunch of other good works and cool works, but we're going to focus just on this specific technique has been used from two different sides, on the binary analysis side and also on the source code. And also at the end, I'm going to give you some insight about the ideas and open challenges regarding solutions for this kind of problems. So as a history, so basically the firmware analysis, one of the best papers that came in Usenix 2013, which was PHI. They basically introduced the symbolic execution so into the domain using the source code level analysis. So just as a recap, so basically symbolic execution tries to run a program in a symbolic domain. So instead of having the references to the memories or to the variables that might be under control of user or might not, we're gonna have those as map those in another domain by having those as some symbolized variables, and we're gonna, so basically instead of having just a static value for that, we're gonna put a symbol and against, so the program is a bunch of if then else in the process of the execution, and we're gonna cover all of those constraints and the different conditions going along the path of execution, and covering all of those as a formula. Then we can just pass this on to a solver engine just to give us some sort of solutions. So there was some other works in this field that might not completely use symbolic execution. They try to solve this problem in other ways. So Firmware is another paper. It came out 2017. I guess it was NDSS, not sure. So they tried to solve a particular problem in firmware analysis, just trying to basically find the authentication bypass kind of vulnerabilities in the firmwares. So the way that you can basically pass some specific hidden values to in some of the fields that then you can bypass the authentication mechanism of the firmware and then log in through the firmware without having the real exact secret password. And so in 2018, so we had two other good works. There have been a bunch of other good works here, so but I'm mentioning some of those for a particular reason because they are sharing something inside. Which was IoT fuzzer, discovering the memory corruptions in IoT through application-based fuzzing. So basically, instead of going through like the MCU, like the chip of the firmware, or even going through the drivers itself. They are working on the application layer. So if we consider like the firmwares that they are sitting on like the some sort of like a middle layer between the hardware and software. So basically these guys are working on the software level, and that software level, which is the application which queries the firmware, and then firmware works with that hardware in the backend. And so this is like another kind of like view to this whole problem set. Yeah. So basically, instead of just taking the firmware out of the system and trying to analyzing that solely, or even another idea, just doing like kind of rehosting kind of things, they are just looking through the program itself that is working with firmware and querying the firmware. And there has been another work which is Avatar 2. So previously we had Avatar and then Avatar 2, so which is somehow completed version, and basically an kind of like a orchestration framework platform to do a firmware analysis, which employs the dynamic symbolic execution, and which works based on anger. And so this kind of things, even Firmalis, it came to use like I used them anger. Anger is the binary analysis platform basically developed in University of California, Santa Barbara, which I'm going to go through that in the next couple of slides. But basically, so it has like a bunch of analysis techniques and tools employed in mostly for dynamic symbolic execution, but we have a bunch of techniques for static recovery and static analysis, and which gonna kind of help us to analyze this binary blob of the firmwares, which most of them basically they don't like resemble a particular specific format that is known, like the executable format for the Windows or Linux, like like the COF format or ELF, or kind of like the PE format. And so another work, so starting in 2019 and 2020, so the academia just looked through this problem in another way by just solving this problem using a new manner of rehosting this like the whole kind of framework, and the framework in another kind of system. So basically, you can think about that of this firmware has like different kind of modules. Each of those modules and the way that they are interacting together can be modeled through some like virtual machine kind of techniques. That basically cloning the somehow not the exact, but some part of the functionalities of the firmware in another kind of domain, that basically instead of just trigger kind of, like fuzzing the firmware, the firmware which is on top of the hardware basically over and over, which basically you need to just restart the whole system after every crash happen. So basically in this way you just need to, you have a model of that, and in your system you're just restarting the model, which is quite fast than restarting the system which is working at the hardware system. And so those two works, like one of them is like P2IM, which gonna be presented in I guess Usenix 2020, which is about rehosting the firmware through automatic peripheral interface modeling, so that the ways that they are modeling the peripherals that the firmware is communicating with. And FirmAFL, which is kind of another way of looking through the process. I'm not going through these two, or basic like kind of motivation is about the symbolic execution, and they're trying to solve this problem, but this one is related to augmented process emulation. Okay, so talking about the why and the very base work of doing the firmware analysis, let's take a look at this problem like in kind of more details, what's going under hood. So as you can see, basically in like so FIE was working on top of the for a specific kind of firmware, MSP430 architecture. So they are basically targeting a specific architecture. So these firmwares coming like some of the based on top of some like weird architectures that might not be very familiar for most of us, because they are usually need to perform some sort of like operations which doesn't need a complete whole OS. So basically they have the part of an OS. So they are basically need to be low cost kind of devices with low computational powers. So they have like different kind of architectures employed. So as you can see on the left hand side, it's MSP430, like it's a program wrote for this MSP430 just to work with the specific kind of pins that I'm going to go through that. So this device, as you can see, can have different kind of variations. This is one of the variations. It comes with a specific code afterward, and it has some sort of like ports. It can come. So on this picture, we have just basically two or three pins. So no, two ports, basically port 1 and port 2. But this device can come up to 6 ports. So different variations. This variation just have 2 ports. And so basically there is, as you can see on that kind of while loop that we have in the firmware, if the pin 1 input has been set, so basically get the pin 1 in as the length, and then it's activating some sort of interrupts, and then it checks. So when the interrupt activated, there are going to be some branches in the code, and if the pin is not set, so basically if there's nothing in that, nothing put into the input of that, so then call str and copy with DST source and length. So this can be like a obvious case of like having a controlled, unbounded kind of use of str and copy, because the length is under the control of the attacker or user. So there are a bunch of challenges just to applying symbolic execution purely on this one. If we just apply the naive symbolic execution kind of technique on top of this code, we basically are not going to get very good coverage. Why? Because there are a bunch of challenges here which has not been covered for the firmware analysis. So the first thing is that all of those pin 1, the different kind of values you can see for that. So each pin, so each of these ports, basically, so each of those ports can have like different macros assigned, and those are like mapped to specific memory locations. Which, for example, for this specific one, as you can see for the port 1, there are like 3 different statuses for that, like the in, out, and the direction. So as you can see, like these specific things, in order to for the hardware to like kind of communicate, in order to for firmware to communicate with hardware, this kind of ports has been mapped to specific memory location. So these kind of things, as you can see, these are offsets or in some part of the memory. So offset 0x20 or 0x21 for pin 1, port 1 out, or the direction of that. Each of those gonna be like the 8-bit kind of values in that memory location. By just purely applying the symbolic execution on this, we are not going to cover some specific things that I'm gonna cover here. For example, the first challenge here, the architecture diversity. So as you can see, the pin 1 in and some of those, so in the assembly 1, so they are mapped to specific memory locations. But basically, we do not have access to those memory locations, and from the naive point of view of a symbolic executor engine, those are like uninitialized memory locations. Okay, so basically, it means so we are trying to get access 0x20, which doesn't make sense for that, and these two are like kind of mutual exclusive. So basically, symbolic execution cannot like cover those. And specifically, so as you can see, as I mentioned, so pin 1 in, so for some of them is 0x20. There are some other variants that this specific address is located in 0x200. So in order just to make it support all of these architectures, we might be able just to basically hard coding all of this stuff, or somehow providing those kind of definitions to our symbolic executor engine that whenever it saw these specific offsets in just this kind of constraints that we can see on the code, so just consider that one like as a symbolic memory location. And so the second challenge, there are some semantics here. So basically, when I say that this specific port input has been set, it means something is coming out of this. And when it's not set, so basically it's like we set. So we're gonna have one of these two at a specific particular point of time correct, and it cannot be both of them correct. But for example, if this one is correct, so this one is not correct, and so we need to kind of telling the symbolic executor engine to consider this specific semantic on the hardware level as human can understand it. So and the other thing is that these kind of programs, so they are receiving interrupts, and so basically from the outside world. So through the, so interrupts gonna interrupt the CPU that is working on the back end, and they are just giving some sort of commands to the CPU that, for example, wait for this specific amount of time. And these interrupts can change the control flow of the program that we have. For example, here that we are activating the interrupt. So this is a while loop. So every time it's running. The first time we are going through this might has been set. The second time we are going through the other line. So at any point of these, instructions, we can jump to the interrupt service routine, which is defined here. So basically, there are a bunch of kind of conditional jumps based on the values coming from the environment as interrupts that can change the control flow of this program. Okay, so these are like kind of complications and challenges that this paper tried to address as the base paper for analyzing the firmware. So their architecture basically, so they are working on the source code. So they are taking the source code of this firmware and they are trying to compile that using the Clang. And so they just, so they are compiling through the Clang, and Clang will provide you a bit code, a LLVM bit code. And so on top of that bit code, you can have like symbolic execution based on that kind of IR that you have, because this like LLVM is an intermediate representation that you can have a unified model for all of the different architectures and different assemblies to a unified model, which is the intermediate representation or intermediate language, and you can have your semantics on top of that. So as we mentioned about the challenges on the right hand side, so their symbolic execution engine, which is CLE, has been added some other stuff on top of that. For example, in order to fix the problem of the peripheral semantics, they have this memory specification, and interrupt-driven programs, as I mentioned, the jumps that can happen, they have like interrupt specification, and also the architecture diversity as regarding that is analysis specification. So let's go again through the code and see how this kind of three modules that they have added to their symbolic executor engine can change the way that the framework can work and find the vulnerabilities in these kind of programs. At first, the analysis spec, which tries to solve the architecture diversity. So we need to provide like some sort of like the memory, the base memory address that a specific firmware should load, because these firmwares, as I mentioned, they are some like the blob. Like blob is like a binary kind of file that it doesn't have any specific format or shape, and you don't have any idea about which specific part is the entry point of the program. You don't know the base address of that. Even at some point, you don't know even the architecture of that. So you need to just go and find ways to make it simplify. So basically, for this specific one, they consider that they know where actually that memory location is located. In other paper, Firmalis, we're going to see how they can use some heuristics to find those specific memory locations. They define different ranges. So as I mentioned, these kind of ports, the hardware ones, should be mapped to some specific location into the memory. That basically this kind of mappings is used from the firmware side to just take some of the stuff from that has been set through the hardware. So the hardware, like something coming through the port 1 as the input, and the direction is also input, and then it can take that specific value through the mapped region into the memory from the firmware. So these kind of regions, which is kind of from like start range and end range, is like considered to be as flash, or might be EEPROM or different things. And so for each of those pins, like ports. I'm saying pins and ports again. So for each of those ports, we have those addresses also set. For example, for the port 1 we're gonna have this specific, like the index in the memory, which is 0x20. But as I mentioned, there are a bunch of different kind of specs, variants for this MSP430. They have solved this solution, the problem, by going through the MSP430 GCC backend, and they parse the header file of this whole compiler to have all of the different versions that is possible for the compilation of this kind of code. So it's another way of solving kind of these problems, just using the information that are available. And then as you can see, also they are mentioning the interrupts. So we need to have the interrupt service routines that change the control flow. So after the interrupts has been activated, at any other execution on the each of line of code, we can divert the execution to one of those interrupt service routines based on like the environment specific variables has been set. So they have this kind of analysis spec for architecture diversity. And so we're gonna have like some idea about 0x20. What does it mean? Okay. And in the memory spec, they're gonna have the semantics of like those kind of like values. So basically, for each of those like the memory locations, we have either read or write. So somebody is reading that specific memory location or is writing something into that. So, and so basically, they have like two functions set for this one, which basically at every point of time. So it's looking for any store or load that has been happened in that specific memory location. So the thing is that, for example, like here, as we can see, so this specific memory location now has a symbolic each time it should receive, for example, for this specific read that we have here or another read we have here, at each point we're gonna receive a fresh symbolic memory. That might be noticed as like an over approximation over the whole possible states that we might have. Because why? Because here we have a constraint, but so in another time we are creating another unconstrained kind of symbolic variable. So this way they are trying just to do an over approximation over all of the kind of possible combinations. And so they are mentioned, which this one can introduce a bunch of false positive in their work, as they mentioned. And so as you can see, so in this way, so when we are reaching to this if, so there is a difference between these two right now, because at each of these points we are creating a new symbolic memory location for each of those reads. Okay, so for that specific index, so that index is related to a memory location, and they are creating a symbolized thing for the value that is being read from that specific location or being written to that specific location. And so this way, so we're gonna have like, and also there's another question that, is it possible to have the symbolic targets? So like, can we have some of those locations that you can write into that, but it's the right address, the reference of that being a symbolic variable, so which it means that you can actually write in any particular memory location that is under the control of the user. So any
Hello? Somebody online who has a question? I think they are not muted. Matt could mute them.
Oh, well, Matt's gone to lunch. Could you please mute?
Okay. So I can continue that.
You connect from your computer?
It's my computer, yeah.
No, but if you connect to Blue Jeans from your computer, no.
No.
Okay.
No, whoever's dialed in remotely should be able to mute.
Yeah, if they hear us.
Oh,
Sorry for the interrupt. So,
no, it's not your fault that somebody who's online.
I'm going to continue on so basically for the memory specification, as I mentioned, again, so we have this like MMIO operations, okay? So basically, like GPIO is one of those peripherals that when you are connecting to your like device, yes, so it can like assign a specific particular kind of memory, part of memory to GPIO kind of peripheral. And when you are connecting SPI, on the runtime, there is another assignment for the specific part of memory for any read and write based on those like directions and like in and out to that specific port. So in this way, firmware can get an understanding about the things that it can receive from the outside world. So in this way, they have this like memory modeling or memory specification. So for each of the pins, they have the read and corresponding write function. And regarding the interrupt-driven programs, as I mentioned, so if this one gets activated, so at each of these particular points, we can have like jumps to different part of the program or this code. So basically, so this one, when this guy get activated, starting from here onward and any part of the loop, we might actually have this interrupt service routing enabled if we have something on port 2, which in this specific case, so actually in this particular time, we need to check that if this port 2, the direction activated for in or out. So if the in has been activated, it checks for like that. In this interrupt service routing, basically it needs to mention that. So it's for the in or out kind of operations that needs to trigger.
And I guess symbolically you can't really tell the difference, right? Because it has to be both anyways.
Yes, it's also, yeah. But actually there are three kind of them, in, out, and the direction. Yeah, so they are like different.
So a quick question here, like I read this paper a long time ago, but it seems to me that just like branching at every instruction because there might be an interrupt triggered is not the most efficient way to proceed here, because there could be, like if you think about it, anytime you have a program statement that depends on one of those memory mapped I/O values, that triggers an interrupt when the value arrives, which is basically what you were explaining.
Exactly. So basically they mentioned this one in their paper also, your concern, and that's a good question actually. So as you can see, as I mentioned, they have like an over approximation, and they are considering attacker as an attacker has access to any port at that specific time and any interrupt.
I mean, that's probably okay, but my concern here is why don't they, like you could say, we don't really care if there's been an interrupt if no one reads that value, like you could like compare the data dependence between your, sequential program that well, it's not really sequential, but you can model it as a sequential program.
Yeah.
And then when you have a value that actually depends on those interrupts, now you can say, okay, there's an interrupt.
Oh, but the thing is that, so for this particular case, so 0x20, so in the mapping that we had, 20, 21, 22. So 22, changing the direction here. So the 0 means the direction out, and 1 means direction in. So basically, in the next loop, we're going to have like some sort of another kind of arrangement with the regarding the way that it considers the in and out, because it changed the direction for that specific port.
Assuming it can only change direction once per cycle?
This one, when this one has been activated, so this one is gonna be just for out, okay? So basically, if this one activates, so anything comes on port 2, that is like value comes to the port 2, then it's gonna change the direction for the port 1 to 0 means out.
So you can do that once per cycle, basically. So you cannot do
For
that
the first one, we are going for the
What I mean by cycle is like instruction cycle at the CPU level.
So we consider it is running like sequentially, yeah. So
if you think like, because this microcontroller probably just executes one instruction per cycle anyways. So if you go, one cycle, you can read that value and switch the port,
you mean direction. As a simplification, just not having that over approximation over the whole state, yeah. Because because right now that the way that they are working is that they have these spawn interrupts. So spawn interrupts, it works on the instruction level rather than working on the basic block level. So on the instruction level, so they are checking that for all of the interrupts has been introduced in the system, like the interrupt service routines, or any other kind of interrupts that is usual for the device itself, because device itself also has some sort of interrupts. Then it checks if the interrupt is on or not in that specific time segment. And then the priority or preemption, it checks because the interrupt preemption, there are the priorities for the interrupts. So might be some of the interrupts are not, doesn't have higher priority. So
they have a model for that in Phi?
Yes, yeah.
I didn't remember that.
I actually go through this one. So in the next slide, I'm going to talk about, basically right now, as we can say, so for example, when they are checking through the span interrupts gonna produce like a flag for us for each of this for instruction. It's gonna go through all the gates. Basically, they are introducing gates, and those gates basically are those like interrupts that they are checking. For example, on port 2, if it's on, and checking the priority of that specific interrupt. Then they create. So it checks if it can create the somehow the interrupt state or not. So what's the interrupt state? So interrupt state is the very first instruction in the interrupt service routine. So basically, if the successor by applying that interrupt can be another state, the very first, so the PC gonna go to the very first address of that instruction in that ISR. And then this one, so the F flag, it means should execute or not. So what does it mean? So it means, so there are some points that program should only rely on the states that are coming from the interrupts. For example, consider system is going through the halt mode or sleep mode. The only thing that can wake up the system is at a specific time elapse, okay? And so basically right now, the successor state or the list of the active states, we don't have any instruction going through that. There are some, so on the scheduler for the symbolic executor, we need to pick one of these kind of interrupts and then changing that one as one of the active states that we have. Okay. So I will go through this one in more detail. So as I mentioned, so they have this, so running the symbolic execution, so it's very useful because, it's complete. So you can completely kind of, analyzing and assessing a specific model. But the thing is that it suffers from two basic problems, which are not basic, but basically, the hard problems that based on the way and the environment you are trying to solve that problem, somehow you can combat those, which I described. So one of them is a state space exclusion. When you are adding a bunch of kind of redundant states into the list of your active states, it's gonna generate a bunch of states, and your scheduler stuck at. So it should take one of those. It's a queue. Take one of those, go through that specific path, and then when it finished, taking another one. And so, as you can see here, so at the beginning, so before adding any kind of optimizations that I'm going to talk about, it's like this. So list of active states, which at the very beginning, so AS or active states are the very initial states that we have. Consider like the first kind of instruction we are trying to run. And then, so since we are like stepping through this kind of code, if the interrupt has been activated, then we're gonna, someone is dying. So we're gonna check the set of the interrupts. So the set of the interrupts is coming from the spawn interrupts that we saw here. So the spawn interrupts at any point of the program.
Whoever's dialed in has their camera on.
Okay, it's kind of okay. So spawn interrupts basically is looking through that. So for each particular part of the program, checks for that interrupt has been activated or not, and if it's activated, so what state should it generate, and also if we should continue execution from this point onward or not. So there is a flag for each of those, should execute or not. So should execute 1 means that we should actually execute the very next instruction, and should execute equals 0 means we should go and figure out with the interrupt. And so interrupt, because of the preemption, should be applied first. And as we know about the interrupts, so the whole interrupt service routine, we are not going through that, but if we are going, it's kind of considered not good word for that, because atomic might be just for specific instruction, but the whole routine gonna be run atomically and completely without any kind of another interrupt in the middle. But if for sure somebody presses this power button that is trying to shut down the whole system, that's the super high prioritized kind of interrupt that shut down the whole system. So, but in the specific case, we are considering the firmware source code. If you go, the firmware codes, it's not like a binary code, like a very huge kind of code. So this kind of like state space exclusion can be solved, can be resolved using some specific optimizations, which is not possible to be addressed in kind of like regular softwares that we have. So the two kind of optimizations they are using. So let me just finish up with this one. So the list of the active states that we have is coming from the active states, which the very beginning of is the initial state, and then union of that with the set of the interrupts that we have that has been introduced. So again, at each instruction, it checks all of the interrupts that can be activated, because the attacker model, it can access to any kind of interrupt. It can activate any interrupt. And then there are a bunch of kind of states popping up into this list. And the eval is the very next instruction after the current instruction we are running. Okay, so it's kind of that one. And so here we have like the successor states. Instead of going directly through the active states, symbolic executor engine takes the state that needs to run and schedule from the active state. So it's like queue. And instead of going through the active state directly, we are postponing it and just taking a look by having some sort of filter to optimize. So this filter optimization has 2 levels. So the first level is the pruning, which we kind of try to prune the based on the specific logics we have, and memory smudging. So first, we have the successor states, a bunch of states. So for each of those states, we take the PC for that state. So same as this thing we have in Anger, like in the history of a specific state, that we check the PC of that state and checks if we saw with the same PC, for the same PC of that state, the same kind of variables or not. If the state variables, like memory, a bunch of things that we have based on that copyright, are similar, so it means that we saw this state previously. So it's just an assertion for the next part of thing that I'm going to talk about, like what 2 states are equal. So as you can see, again, the same code. In firmware is just running, and it's somehow in a kind of loop, yeah? It's always looking for some specific input coming from user. And so it's waiting for input. It receives the input, do some process on that, and then release, and then it's still in the loop, waiting for another input. So this while, basically, it's kind of as we can see, I mentioned a number of each of those lines as this kind of control flow graph that we can see. So one from the while, and then we can go through this if or the other one, and then we can activate the interrupt in the 4, and then going through the 7. This is the first one. But after we activated that one, the next state into this loop gonna be something like this. From any point, we can go through the interrupt service routine through the 8. So it's like a very complicated kind of graph. But we can actually do a pruning based on the fact that, so on each of these kind of, since we think that attacker can activate this kind of interrupts at any specific instruction. So we consider that interrupts is activated, and we are going through this code. We find that, okay, we have this while loop by just going through this one. I just mentioned the colors. You can see this red one, and I noticed the red one, the same state previously. So I'm just kind of adding some kind of redundant states each time that I'm going through that specific loop again and again. So this way, then I can prune this whole tree instead of just continuing that one to this level, up to this level, just to have this part of this kind of graph. So we're gonna check for the pruning. We send a PC this one is the PC, yes. So that's a PC, yeah. Basically the PC of this state and the state itself, and to check if we have like the similar states in like the execution or not. So basically we're kind of logging the whole like the execution kind of time. I mean, we are logging the whole execution, and we are going through the log to find like we have this kind of similar states or not. So then about smudging. So smudging is another technique used. Take a look at this code. So we have this kind of while loop that it just increments by 1 the variable I up until it reaches to the maximum long. But the thing is that, so if we just try to run this one in symbolic execution manner for this I, so we are just adding a bunch of redundant states because of that, the interrupt activation, as I mentioned. So the interrupt that are activated at this step in this while gonna like produce a bunch of kind of states, which are, most of them are kind of redundant. So the smudging works by adding a bound on this kind of while loop that we have. So this bound gonna decrease the iterations to a specific amount. Like here we have like 100 that has been set. So basically k1, k plus 1, k plus 2, and k plus 3. We go through this one, we have this loop here, and by just doing this smudging, so we're gonna somehow take a look if we have some variable that has been being changed over the process of time, then we are trying to somehow symbolize that one. So basically considering a specific amount for that, 100, and then anything which is not 100. Okay, so this way we can add another state, which is the state next to, after this while. So while finishes here, so we're gonna add one more state here. So this one might look that, okay, we are adding one more state to the whole number of the states that we have, which can help to the completeness of the analysis. But the thing is that the pruning can do its job, and for this specific particular loop until from I1 to 100, it can just find that, okay, I'm just running the same thing over and over. So basically, we're going to end up with this kind of graph, state graph. Yeah. And so
you're like adding different states after executing, like reading one instruction.
Yes.
And like you may add more states because you may be interrupted at any time. So you got
exactly. So active states that you can see at each of these like locations, that we have like whole set of active states. So
is it possible that the interrupt is like within the, like for example, you're comparing in the if statement, right? Will it be like interrupted while it is comparing?
So on this part, yeah, there might be interrupt, yeah. So that's why, I mean, I'm mentioning that's why. So here it can add a bunch of redundant states. I mean, the interrupt states, let's say the whole set of interrupt states at that particular location. Okay. And these are going to be a lot of states generated because we have a bunch of interrupts. For sure, this kind of hardwares, they have like a bunch of interrupt service routines and interrupt codes if you go through their manual. Okay, so the next paper, so we finished with Pi, which they did basically simple execution on source code. We are going to look at the same problem, but harder problem to solve on binary analysis. So as I mentioned, Anger is the basis of this, like the framework, of this paper on this work. And to detect the specific kind of vulnerability, which is the authentication bypass. Let's take another look again to this like schematic of the way that so an MCU like the microchip has been working. So we have some on-the-chip peripherals and also off-chip peripherals. So off-chip peripherals like the LEDs, like the actuator, gyroscope, or a bunch of other stuff that are connected like physically through this to this kind of, let's say chip that we have. Okay, because if you have a chip, it's like a board, and you have different kind of this peripheral. This kind of off-chip peripherals installed on top of that, like LED, gyroscope, and they are communicating with this whole chip. And inside of that, for sure, we have like CPU, memory, and memory manager, and on-chip peripherals. So as you can see, there is a proxy here on-chip peripherals. So this proxy makes a proxy between the inside peripherals we have that are like, GPIO, which are kind of MMIO kind of peripherals. And as I mentioned, in order for chip to get access to those specific stuff has been set through these off-chip peripherals. They're going to map it to a specific memory location. This is the region that I was talking about. This is the region in memory for that memory mapped IO that, for example, the GPIO might be mapped to one of these like locations. And we have different kind of ways to communicate with the MCU. Like some of them are through the mapped basically registers, which are the MMIOs that we have. So we have like some of the registers, like 8-bit ones that we had previously, has been mapped to that specific memory location. Or we can have like interrupts. So basically, interrupts are coming from the like outside to interrupt the CPU, and the registers or MMIO that we have, CPU is writing or even reading some stuff from that to communicate with the other part. So this is like the way that they are communicating. And sometimes also we have the direct memory access DMA, so which can directly go through the memory page and get access to that and read a specific thing from the memory itself. So with this thing on top of mind, so the way so this paper works, we have like consider for a specific kind of router. This one is a D-Link router. So they are trying to detect authentication bypass. So authentication bypass considered to be something that we know as backdoors in the system. Okay, they are trying to find backdoor. So backdoors are, basically any kind of authentication can be kind of like strcomp with might be some hard-coded string value inside this binary code that we have, which is one of the most popular cases that we can see. So strcomp, Or some of authentication bypasses can be like a hidden page. There is a hidden page on this firmware. If you go to that specific page, then you can see like I mean, not shell for sure, but like you can, so there's a vulnerable PHP application on top of that you can communicate with those. But why actually these backdoors are in the systems? So are they intentionally put it there? Yes, but for which reason? Sometimes they want to automatically come and update your firmware, okay, remotely. They need to somehow get access to your system. Myriad and some of these bots, some specific variations, are using this kind of techniques to basically subvert this kind of I'm not sure if I should say like usual behavior or not, but I mean from the vendor side, it's a usual behavior just to have these backdoors might be inside, but they are trying to misuse that and basically running an attack on the users. As you can see in this specific part of code, sorry, how much time do I have left?
What time is it?
It's almost
3, so that was supposed to be in 1 hour. We started a little bit late,
We're-
so he needs to start trying to wrap up.
Yes,
Okay.
we're running short.
Okay, sure. And so as you can see, like in this specific part of code, so we have like, so the one that I mentioned here, HTTP request, this is a struct S0. By reversing this firmware, we found that, okay, in HTTP request T struct, there are two kind of elements that are important and particular interest of us, which is element has at offset B8 and D0. So B8 is known to be URL and D0 user agent. So as you can see, like, so we have B8 here and D0 here. So the B8 is the URL. So it's checking for some specific values in the URL itself. So like the graphic or public in the URL, in the URI of the request, including for the D0, it's user agent, some specific hard-coded string into the user agent. And then we go through the graph of this, like the execution. So this one is about the authentication process. And sorry, it's in red, might be not readable. So basically, it's alpha authentication check. This part. When you go back through the program, which this going back through the program, we're gonna know that one as a slice of the program. So we go back and we find, okay, so this part is interesting for us because there's a strcom, which the value is under control of user. I mean, it's coming from somewhere that is under control of user agent that you can send it through the request. And it's compared against some constant value. So then, and also it's using the strcomp or strncomp, this kind of variations. Find this one, so they're gonna create the CFG of that of this like for this firmware, and they're gonna go backward, like the backward slice, take a slice of this portion of the code, and then symbolically run that to find that, okay, so that kind of relationship between the values under control of user and this constant to find those specific kind of backdoors. So that's the whole idea behind the way that Firmware is working. And yeah. Okay. There have been two novelties used in this paper. One of them is base address determination. So I mentioned that all of these firmwares needs to be mapped in a specific kind of part of memory, and that is a base address. So these base addresses, so they are looking through the firmware, they are trying to find the jump tables. So the jump tables, as you can see, so there are some of the addresses like the stacked near each other in a specific memory locations near together. So as you can see like this, and they only have differences in some of their less significant bits. So they find these kind of things that range in the address, can be part of an address, and also difference in this specific order in their less significant bits, most significant or similar. And then this gonna be a way that they can find the base address. So they have this one, so they have like the location for the jump tables, and then they go through the references of these jump tables to find the base address of this like firmware. And they also have the entry point discovery, which goes from function recovery and then creating a call graph, since we are going short on time, so just passing this one. And so the good thing we have like in Anger, so we have like VEX, which supports this kind of architectures. As you can see in the first paper, they have been working on MSP 430, which I guess we should have, VEX should have or not. I think
I don't think Vex supports it
yes,
directly.
it doesn't have. I think so.
But I think Eric might have been working on.
We have the GMAT lifter to lift the stuff. Okay, yeah, but it's not very complete. Vex is one of the IRs that Anger is using that to just kind of create that intermediate representation for the. So we have like this kind of assembly instruction, and we convert it to Vex. Just that return gonna be this verbose, and describes like how exactly things on the stack is changing and the PC change and stuff. We can also work on TCG. TCG supports much more architectures. Some weird ones you can see on this, like Chris and ARM64 and Extensa S390X. And so we started this project, like the PyTCG for the Anger, and this can somehow, help to support and for the binary analysis to like kind of support the high range of the architectures, for analyzing firmware. And yep, so this is the result of the VEX. And okay, thanks. That's the end of my presentation about the firmware analysis. And just by going through the two kind of relevant good works that we have, and it's possible to start work on top of those. And I'm open to any question you have.
Besides the microcontroller MC 430, did you try in any other microcontrollers?
Sorry?
Besides that microcontroller, MCP 430,
Yeah, exactly.
did you try in any other? Do you have any other microcontroller also you have targeted?
The other types?
Yeah.
I mean, it's not always need to just have microcontroller. There are like some of the firmwares available. So for that specific particular architecture, that you might, that's an acquisition of the firmware. That's a kind of different topic, but more like kind of engineering topic. That how you can take those stuff. But just thing is that I have a bunch of those, like the different kind of these firmwares.
Did you try in any ARM-based architecture?
There are a bunch of actually ARM-based. So most of them are like the ARM-based kind of firmwares. For example, for the routers, as you saw for the D-Link one, was ARM Cortex. And so, but there are some of those NSP 430, and some of the weird ones like the, as you can see on this.
So regarding this, you mentioned PyTCG. So is it something you guys have been working on, like porting, QEMU?
Yeah, so there was like a course, and so Matt Borgerson and me started that one. So, and then after finishing that course, so we finalized that with like PyTCG wrapper for this kind of, TCG is the IR for the QEMU. So just to introduce that, this is a tiny code generator or generation. And so right now we have this wrapper on this Python. So we are also going through like adding this one into the Anger. So like there's a branch for that to kind of port this one like a heart surgery to, as I mentioned.
So what do you guys want to do with this? Like, where are you?
So we can for sure support like more architectures with more architectures. So I mean, we mentioned the techniques that has been on top of the open source semantic execution, and having those stuff being applied to the binary analysis. I think it's a quite interesting talk that I haven't seen in the papers that I went through. And the problem that they had, so like writing the lifter, like the way that we are writing gene rat lifter, it's not very accurate because we are not hardware guys, we are not architect guys. So we are just having an assumption of what's going on in that specific return. But instruction level, the cycle base, and all this stuff, we don't know. And then writing it by your hand, so it's not very accurate. So that's why we haven't decided to go for like TCG to have like better support. So for future research, like after having this TCG in Anger, so just have, doing the same kind of optimizations have been previously introduced on the source code on the harder problem, which is binary. For sure, it's far, far harder than what.
You should probably say that in that slide.
Yep. Yeah, sure.
And in terms of like longer term, like firmware research, like what's your next step? Like which ones do you want to?
Basically, the reason I selected this talk, I started like this collaboration with like another company, and like AV company, like back in like 6 months or a year ago, and we have been working like to applying symbolic execution on in like kind of the largest scale for the industry, just to find like for the specific reason of bug finding and vulnerability discovery. And so the next step for me, so I'm trying to introduce this like the PyTCG port for Anger as like a project for the Google Summer of Code. I wrote something, I sent it to them, and it's under review. If they accept that one, then we can have 2 interns, I guess, for that specific project that specifically working on completing this kind of integration for Anger. And for sure,
is it like about integrating TCG entirely into Anger?
Completely, yeah. So
having those bridges with QEMU, or do you want to use QEMU as like a concrete execution model in Anger, or?
For sure, Anger has that like QEMU port just for some specific concretization. I think at some point we had an analysis technique on top of that. I just forgot the name. And but this one is just for the dynamic symbolic execution. So basically, not the concrete running on the accumulator. So for sure, it's possible, just to applying this one on top of like the rehosting one, and then like going through that path also. But given the goal you have, the more kind of effort you should have. But this one, so the whole like having this wrapper like might be easy, but porting this one, it's like kind of like easy task to go for it because of the specific kind of differences between the architectures that we have, like the way that ARMs like work with stack and like x86, and the different kind of fast call, STD call, and so how they actually affect this stuff. And yeah, so this kind of part is like engineering effort, but can be like toward this like academic kind of research by applying kind of those mechanisms mentioned in like some of those other papers, just to scale the symbolic execution for this particular problem, because they are not so assumptions that based on this what we saw, it's much the size of this applications are less than usual programs.
Right. Are there any more questions? Otherwise, we'll take a small break.
We have a lot of people online. Anybody else online have questions?
Yeah. Okay. Do you think I should open it?
Okay. Thank you.
So we'll thank you. Sorry. Yes. Thank you. We'll have a small break.